After studying this chapter, you will be able to explain how heat travels, describe how a substance changes state, describe the three physical states of matter, explain a BTU, define specific heat, and explain a ton of refrigeration. The term cold describes a lack of heat, or a condition produced by removing heat. Most people think of air conditioning and refrigeration as cold, or a cooling process. However, these systems actually remove heat from where it is unwanted and carry it away to be discarded. To accomplish the cooling process, the heat must be removed faster than it enters, just like bailing water from a leaking boat. To answer the question, click on the correct button and a pop-up window appears regarding your answer. The pop-up window disappears in 3 seconds. Heat is a form of energy and is always in motion. The second law of thermodynamics states that heat always travels from hot to cold. How fast heat travels depends on the temperature difference between the two objects. The greater the temperature difference, the faster heat travels. Since air conditioning deals with the movement of heat, it is necessary to know how heat travels. There are three basic methods by which heat is transferred from one substance to another: radiation, conduction, and convection. A combination of these methods may also be used. Radiant heat is the transfer of heat by waves similar to light waves or radio waves. It does not heat the air through which it passes. Radiant heat is absorbed by objects, not air. On a sunny day, the interior of a closed car is quickly heated by radiant heat from the sun. Conduction is the flow of heat through a substance. Most metals conduct heat very well. Copper and aluminum are excellent conductors of heat, and these metals are used frequently. Poor conductors are called insulators. Some examples of insulators are polyurethane foams, mineral wool, cork, and glass fibers. Convection is the flow of heat by means of a carrier, normally air or water. Convection can be either natural or forced. Natural convection involves slow currents of air and is effectively used in many air conditioning refrigeration systems. Forced convection involves the use of fans or blowers. Pumps are used for circulating hot and cold liquids. The definition of a British thermal unit is the amount of heat required to change the temperature of 1 pound of water 1 degree Fahrenheit. It is important to know this definition because just like a ruler measures distance and a pound measures weight, a BTU measures heat. How many BTUs are required to raise the temperature of 10 pounds of water from 72 degrees to 82 degrees? Go ahead, test yourself. Click on the correct answer. That's the correct answer. You get a gold star. Click on the button that has the correct definition for a BTU. Now be careful because I tried to trick you. Very good. That's the correct answer. What is specific heat? Well, the definition is the amount of heat required to change the temperature of 1 pound of a substance 1 degree Fahrenheit. A British thermal unit deals with 1 pound of water. Specific heat deals with 1 pound of a substance. The engineers have already discovered the specific heat per pound for all known substances, and the specific heat tables are available at your local library. We have provided you with a partial list of these specific heats, just to give you the general idea. Atoms are pure substances, and molecules are made of atoms. For instance, it requires 2 hydrogen atoms and 1 oxygen atom to combine and form a molecule of water. These molecules are always in motion, and the speed is determined by the amount of heat energy they contain. Molecular movement in a solid is rather slow, and the molecules primarily stay within the confines of a solid. In a liquid, the molecules move faster because the liquid is warmer than a solid. Again, the molecules primarily stay within the confines of the liquid. As a gas, the molecules have absorbed more energy and move rapidly in all directions. They are not confined by any borders. Most substances can exist in three physical states: solid, liquid, or gas. As heat is added or removed, the substance will change temperature or physical state. When a substance changes from one physical state to another, the temperature does not change until all the molecules are rearranged to the new physical state. The same amount of BTUs are required whether adding or removing heat. After studying this chapter, you will be able to define sensible and latent heat, describe 5 changes of state, explain superheat and subcooling, use the 5 refrigeration applications, define saturation point, and explain Fahrenheit and Celsius thermometers. Sensible heat causes a change of temperature, but no change of state. If heat is added and the temperature rises, it is sensible heat. Likewise, if heat is removed and the temperature changes, it is sensible heat. Latent heat causes a change of state, but no temperature change. During a change of state, the temperature remains constant until the change of state is completed. As shown, when ice is melting to water, the temperature remains at 32 degrees until the last bit of ice melts. Adding or removing heat from a substance changes either temperature or physical state. Because ice, water, and steam are familiar to everyone, it is used here to illustrate the principles of sensible and latent heat. Water is not used as a refrigerant because of its high boiling point. The boiling points of refrigerants are often well below zero, but the same principles apply. We have learned that heat must be added or removed to cause a change of state. 4 terms are used to describe the different changes of state. For the latent heat of freezing, heat is removed to change a liquid to a solid. For the latent heat of melting, heat is added to change a solid to a liquid. For the latent heat of vaporization, heat is added to change a liquid to a gas or vapor. For the latent heat of condensation, heat is removed to change a vapor to a liquid. The melting or freezing point of a substance always occurs at the same temperature, but the temperature is different for each substance. Water, for example, always freezes at 32 degrees, and ammonia always freezes at minus 107. The same amount of heat energy is involved in a change of state, whether heat is being added or removed. The same amount of BTUs are required to freeze 1 pound of water as it does to melt 1 pound of ice. This is true of all substances. The boiling or condensing point of a substance always occurs at the same temperature. Exactly the same amount of heat energy is involved, regardless of whether heat is being added or removed. It requires the same amount of heat energy to boil 1 pound of water as it does to condense 1 pound of steam. This is true of all substances. After studying this chapter, you will be able to understand pressures and boiling points. You'll be able to read the compound gauge. You'll be able to explain the high pressure gauge. You will be able to describe 3 methods of measuring vacuums. You'll be able to explain a perfect vacuum from a partial vacuum. And you will be able to use the saturation card. Our planet is surrounded by a gaseous atmosphere that extends about 50 miles above the Earth's surface. The gases that make up the atmosphere are composed of tiny molecules traveling in all directions, but held within the 50-mile area by Earth's gravity. The weight of these molecules exert a downward force, known as atmospheric pressure, upon the Earth's surface. The pressure is greatest at sea level and is generally considered to be 14.7 pounds per square inch. At higher altitudes, the atmosphere is much thinner and exerts less pressure. The pressure on a liquid determines its boiling point. In this example, the water is at atmospheric pressure, so it boils at 212 degrees Fahrenheit. The water cannot get hotter, regardless of the amount of heat applied. It will only boil at a faster rate. The water temperature will remain at 212 degrees until its state is completely changed from water to steam. Therefore, any change in pressure on a liquid also changes its boiling point or saturation point. The pressure cooker was invented to permit water to be heated to temperatures above its normal boiling point without changing state. Placing a sealed lid on top of the kettle trapped the molecules of steam between the lid and the surface of the boiling water. As the space becomes crowded with escaped steam molecules, the pressure increased. This increased pressure prevents the escape of additional molecules. In effect, the water stops boiling. To continue the boiling process, the temperature of the water must be raised to overcome the increase in surface pressure. Thus, as the surface pressure is increased, the boiling point also increases. Absolute pressure, or pounds per square inch absolute, means the zero is placed down where it belongs, where no pressure exists. This is called a perfect vacuum, or 0 psia. Atmospheric pressure is 14.7 psia, or 15 psia. The illustration shows a vacuum pump being used to remove all molecules from inside the cylinder. When a perfect vacuum is achieved, the absolute gauge will read 0 psi. Reducing the pressure on a liquid also reduces the boiling point. With no fire, removing all pressure, in other words, a perfect vacuum, water boils at minus 60 degrees Fahrenheit. This is called flash boiling. The mercury manometer is sometimes used to measure atmospheric pressure. The tube is accurately calibrated because at atmospheric pressure of 15 pounds per square inch absolute will push the mercury 30 inches up the tube. These numbers have been rounded off because technically they would read 14.7 pounds absolute and 29.9 inches of mercury. The chemical symbol for mercury is capital H small g because the Latin name for liquid silver is hydrogyrum. 25 inches of mercury would be written 25 with the inch symbol and capital H small g. Most gauges ignore the vacuum area and place the zero at atmospheric pressure. Readings are above atmospheric pressure and given in pounds per square inch gauge, or PSIG. However, the compound gauge has two scales, with each scale starting at 0, or atmospheric pressure. One scale reads pressures above atmospheric, or PSIG. The other scale reads pressures below atmospheric in inches of mercury. On the compound gauge, a perfect vacuum is 30 inches of mercury. The compound gauge is color-coded blue, and technicians use this gauge for reading the system's low-side pressures. Sometimes these low-side pressures are in a vacuum. The mercury manometer scale and the compound gauge's vacuum scale are reversed. The compound gauge is used by technicians, while the mercury manometer is primarily used by weather forecasters to check atmospheric pressure. Weather conditions are greatly influenced by atmospheric pressure. Most gauges read 0 at atmospheric pressure. They measure pressures above atmospheric. The reading is stated pounds per square inch gauge, or PSIG. The high pressure gauge is color-coded red, and is used by technicians for checking the system's discharge pressures. Micron gauges provide another and highly accurate method to measure vacuums. A good vacuum pump should be able to pull 500 microns. Very accurate low vacuums may be required on special equipment such as cascade systems. All mechanical refrigeration systems are compared to melting 1 ton of ice in 24 hours. This is called the ice melting equivalent, or IME. The IME is calculated by multiplying 2,000 pounds, which is 1 ton, by 144 BTUs. This is the latent heat for melting 1 pound of ice. Therefore, 2,000 times 144 equals 288,000 BTUs in 24 hours. Therefore, any mechanical system able to remove 288,000 BTUs in 24 hours is called a 1-ton system. 12,000 BTUs per hour is universally accepted to represent 1 ton of refrigeration. The gas laws mathematically prove the behavior of a pure gas in a confined space. They show the relationship between pressure, temperature, and volume. With a fixed volume, the temperature pressure of a confined refrigerant can be predicted and controlled. The ability to use the gauge manifold to obtain the refrigerant pressure is a basic requirement. This pressure reading is converted to temperature with a saturation card. Proper temperatures are achieved by controlling the pressure. Saturation means boiling point, and boiling point is determined by temperature and pressure. The saturation card provides both conditions for each refrigerant. If you know one condition, either temperature or pressure, the card provides the other. This is a full-size view of a typical that is available from your local supply house free of charge. This card has 5 different refrigerants, and the card can be folded to fit into your shirt pocket. We are going to know exactly how to use this card. Dalton's law deals with a mixture of gases rather than a single pure gas. Dalton discovered that in a mixture of gases, the total pressure is obtained by adding the pressure of each gas in the mixture. Atmospheric air is a mixture of gases and moisture. Major problems occur if atmospheric air enters a refrigeration system. Most systems are totally sealed and depend upon a single pure gas for proper operation. When a mixture enters a system, the saturation card is useless and acids are formed.
The primary purpose of refrigeration is to eliminate the warm conditions under which destructive bacteria prosper and multiply, and by subjecting the bacteria to conditions of cold, to reduce their rate of activity and growth. The process of producing cold is the process of removing heat. There are 3 methods by which transfer of heat from one place or body to another is accomplished. The first is conduction. When a flame is applied to one end of a metal bar, heat spreads through the metal, passing from molecule to molecule toward the cool end of the bar until the entire bar is hot. In the process known as convection, Heat is carried along by the motion of a stream of gas or liquid whose function is similar to that of a conveyor belt. In conduction and convection, heat is transferred through or by matter. The process of radiation involves the direct transfer of heat in the form of waves, without need for a medium for the heat to move through. Refrigeration makes use of all three methods of heat transfer. Heat quantity is measured in British thermal units, or BTUs. A British thermal unit represents the quantity of heat required to raise the temperature of a pound of water 1 degree Fahrenheit. Of the three effects of heat, refrigeration is chiefly concerned with two. The first effect, that of sensible heat, is one that causes a change in temperature as read in degrees on a thermometer. In this example, as heat is applied, the temperature of the water in the kettle rises up to 212 degrees Fahrenheit at sea level. At this point, the temperature remains constant, and the second effect, latent heat, is observed. The water changes state and becomes a vapor. Change of state may proceed in either of two directions. When a sufficient quantity of heat is absorbed by a solid, it passes into the liquid state. Upon absorbing more heat, the liquid evaporates and changes to a gas. When sufficient heat is withdrawn or released from the substance in its gaseous state, the gas condenses or changes back to a liquid. When more heat is withdrawn, the liquid freezes or returns to the solid state. For any substance, there are two distinct quantities of heat involved in changes of state. The first, latent heat of fusion, is the quantity of heat that must be absorbed by the substance in the solid state in order for it to change to a liquid. Or that must be removed from the liquid if it is to return to the solid state. The other quantity of heat, latent heat of vaporization, is that which must be absorbed by the substance in the liquid state in order for it to change to a gas, or that must be removed from the gas if it is to return to the liquid state. In mechanical refrigeration, it is the movement between liquid and gaseous states that is important. Absorption or release of latent heat does not alter the temperature of a substance while it is changing state. In this example, although the block of ice absorbs a certain quantity of heat as it melts, its temperature during melting remains constant at 32 degrees Fahrenheit throughout the change of state. We know that when a liquid is heated to a certain temperature, it boils and changes to a gas. However, it is possible to cause the same liquid to boil at a lower temperature. This is done by controlling the pressure upon the liquid. The higher the pressure, the higher the boiling point temperature. The lower the pressure, the lower the boiling point temperature. It is through control of pressure that refrigerator temperatures are controlled. We know that heat will flow from the warmer to the cooler of two adjacent bodies, that the flow will be relatively fast while there is a large difference between the temperatures of the two bodies, and will become slower as this difference becomes smaller until it ceases when the temperatures of the two bodies have become equal. When a liquid changes to a gas, it absorbs heat which flows to it from its warmer surroundings. When these surroundings happen to be food in a refrigerator box, heat is withdrawn from it. That is, it is cooled or refrigerated. This is the rock-bottom basis of modern refrigeration.
After studying this chapter, you will be able to name the 7 basic refrigeration components. You'll be able to describe how each component operates. You'll be able to explain the condition of the refrigerant in each component. You will understand how refrigerant flows through the cycle. You will know how heat is absorbed in the evaporator. You'll be able to describe how heat is removed from the condenser. The basic refrigeration cycle consists of 7 components. Some are located inside the building and some are located outside the building. Liquid refrigerant evaporates and absorbs heat on the inside. Refrigerant vapor goes to the condenser and releases heat on the outside. This slide illustrates the condition of the refrigerant inside each component. We will learn how each component operates, beginning with the evaporator and following the refrigerant flow. The inside warm air gives up heat to the cold evaporator metal fins. The metal fins conduct this heat to the liquid refrigerant inside the tubing, which is evaporating at low pressure. The condition of the refrigerant inside the evaporator is low temperature, low pressure, saturated. Heat travels hot to cold, and the refrigerant is the coldest temperature because that's where we want the heat to go. The temperature of the refrigerant is controlled by pressure. The metal of the evaporator is about 10 degrees warmer than the refrigerant. The entering air temperature is about 10 degrees warmer than the evaporator. For heat to flow hot to cold, these temperature differences must exist. The suction line is made of copper tubing and connects the evaporator outlet to the compressor intake. The suction line is insulated and carries a superheated cold gas. The conditions are low temperature, low pressure, superheated gas. As shown, there are 3 types of reciprocating compressors: open, hermetic, and semi-hermetic. Size and manufacturer may vary, but not the type. Compressor operation is fully explained in Chapter 13. The compressor valve plate is one of the division points between low and high pressure. On the piston upstroke, the piston compresses the low-pressure cold suction gas to a much lower volume, which increases temperature and pressure and raises the saturation point. On the piston downstroke, the suction valve reed is pulled downward, and cold gas is pulled from the suction line and crankcase into the cylinder. The discharge valve reed is closed. On the piston upstroke, the suction valve reed is closed by cylinder pressure. The discharge valve reed opens at the top of the stroke when the cylinder pressure overcomes condenser pressure. The hot gas discharge line is made of copper or steel and connects the compressor discharge to the condenser inlet. It carries a highly superheated, high-temperature, high-pressure gas to the condenser inlet. The hot gas discharge line, condenser, and compressor are usually located outside and referred to as the condensing unit. The condenser uses ambient air to remove heat from the condenser and refrigerant gas. Heat removal at high pressure causes the refrigerant gas to condense back to a liquid for reuse. The refrigerant conditions are high temperature, high pressure, saturated. The liquid line is made of copper tubing and connects the condenser outlet to the inlet of the refrigerant control valve. The liquid line is not insulated, but warm to touch. The refrigerant conditions are high temperature, high pressure, subcooled liquid. There are several types of refrigerant controls, but they all serve to meter the correct amount of liquid refrigerant into the evaporator. The refrigerant control is the other division point between high and low pressure. The valve shown is a thermostatic expansion valve, which controls the amount of superheat at the evaporator outlet, normally about 10 degrees. This is the complete refrigeration cycle, showing all 7 basic components. The dashed line indicates the 2 division points between low pressure and high pressure. This is the basic system shown in the operating mode and showing you the difference between the indoor unit versus the outdoor unit.